Look at your hand right now. Whatever shade it is, that color didn't come from nowhere. It came from one of the longest, strangest, most dramatic makeovers in the history of life on Earth. And the wildest part, it wasn't random. It wasn't an accident. It was a survival story, a slow-motion biological negotiation between your ancestors and the sun. And the sun, for the record, was absolutely not playing fair. A surprisingly rude star sitting 93 million miles away that caused all of this and has absolutely no regrets. The answer involves vitamin D, cancer, folate, Africa, ice ages, and ancient farmers who accidentally rewired their own evolution. If you trace the human family tree all the way back, every single one of your ancestors, regardless of where you're from today, had dark skin. Every single one. Not most of them. Not the majority. All of them, without exception. Around 300,000 years ago, when Homo sapiens first appeared in Africa, the entire species was dark-skinned. There were no pale people. There were no fair-skinned populations anywhere on the planet. The concept of light skin didn't even exist yet in humans. Now, think about that for a second. Every person you've ever seen in a history book, every ancient civilization, every mythology, every cave painting, all of it traces back to a single founding population that looked nothing like a significant chunk of the modern human species, which means at some point in history, something happened, something changed. And that change was so powerful, so deeply embedded into our DNA, that it reshaped the physical appearance of entire populations across multiple continents over tens of thousands of years. So, what was it? Well, before we get to that, we need to understand something about skin itself, because most people have absolutely no idea what skin actually is or what it's actually doing for you right this second. A lot of people treat skin like it's just packaging, like it's the bag your body came in. But skin is an organ. Your largest organ, in fact, and it's doing about 47 different jobs simultaneously. Most people have no idea what their skin actually does, or what it's doing for them right this second. A lot of people treat skin like it's just packaging, like the bag your body came in. But skin is an organ, your largest one, in fact. It does about 47 different jobs simultaneously, most of which you never think about or thank it for. One of those jobs is arguably the most important: protection from UV radiation. UV radiation is the invisible energy the sun fires at Earth constantly and relentlessly. UV light breaks chemical bonds, damages DNA, and causes mutations in your cells. If those mutations pile up in the wrong places over enough time, they turn into cancer, specifically melanoma, one of the most aggressive forms of skin cancer in existence. The pigment that gives skin its color is called melanin. Melanin is, in the most literal biological sense, a natural built-in sunscreen. The more melanin your skin contains, the darker it appears, and the better it blocks UV radiation. Dark skin isn't just a look, it's a shield. In Africa, where our species originated, sitting directly under some of the most intense UV radiation on the entire planet, evolution selected hard and fast for dark skin. Having more melanin meant your DNA was better protected from the cancer-causing mutations that UV light triggers in your cells. It meant you lived longer, stayed healthier, and were more likely to survive long enough to reproduce and pass your genes to the next generation. Natural selection is basically a very slow, very ruthless optimization algorithm. It runs one calculation over and over again, billions of times across billions of organisms. It doesn't care about aesthetics or beauty. It only cares about one thing. Does this trait help you survive long enough to have offspring? If yes, keep it. If no, eliminate it. That's the only rule. In equatorial Africa, under that blazing sun, dark skin was a hard, emphatic yes. But here the story gets genuinely, unexpectedly complicated. UV radiation doesn't just attack your skin cells, it also attacks something small and invisible inside your body. If you destroy it in the wrong person at the wrong moment, it can end a pregnancy before it even really begins. The molecule is called folate. It's a form of vitamin B9, and it flows through your bloodstream doing essential biological maintenance work. Folate, a form of vitamin B9, flows through your bloodstream doing essential biological maintenance work. You might think, okay, a B vitamin sounds like something your doctor told you to eat more of. Why does this matter for skin color? It matters enormously, especially if you are pregnant or trying to become pregnant. Folate is critical for the development of the neural tube in embryos. The neural tube is the structure that eventually becomes the brain and spinal cord. Without sufficient folate in the first few weeks of pregnancy, sometimes before a woman even knows she's pregnant, the neural tube can fail to close properly. The consequences are catastrophic. Neural tube defects, severe developmental abnormalities, miscarriage. Here's the problem. UV radiation destroys folate. When UV light penetrates the skin and reaches the bloodstream, it breaks down folate molecules. In a sun-drenched environment like equatorial Africa with no clothing, no shelter, no sunscreen, UV exposure was constant, intense, and unavoidable. Pregnant women with lighter skin, less melanin, more UV penetrating deeper, had higher rates of folate destruction. Higher rates of folate destruction meant higher rates of neural tube defects. Higher rates of neural tube defects meant fewer surviving offspring. This created a devastating selection pressure. So now we have two independent reasons why dark skin was so heavily favored in the African sun. First, melanin acted like a built-in sunscreen, shielding DNA from UV damage and slashing the risk of deadly skin cancer. Second, melanin protected folate in pregnant women, preserving the development of their babies' brains and spines, two completely separate threats, and evolution found one elegant solution: dark skin. In Africa, under that relentless equatorial sun, dark skin wasn't just useful, it was essentially mandatory for survival. Dark skin had become a multi-purpose biological superweapon, blocking both cancer and reproductive disaster at once. It had been field-tested and optimized over hundreds of thousands of years, proving its worth in the harshest environment on Earth. If evolution had a review system, dark skin would have a 5-star rating with thousands of glowing testimonials. So given all that, why did it ever change? Why did some populations end up with lighter skin? The answer is one of the most elegant, brutal trade-offs in all of evolutionary biology. Between roughly 70,000 and 100,000 years ago, small groups of Homo sapiens began leaving Africa. It wasn't a single dramatic event. No one organized a meeting or announced a great migration. It was slow, generational drift. Each generation moved just a little further than their parents had, a slow drift that over millennia stretched across continents. Over thousands of years, humans spread through the Middle East, into Europe, across Asia, and eventually into the Americas. And as they moved north, something fundamental about their environment changed. The sun got weaker. Not the sun itself, but the angle at which its light hit the Earth. At higher latitudes, sunlight passes through more atmosphere before it reaches you. UV radiation gets filtered out, days become shorter, and winters stretch long and dark. The UV environment in northern Europe and Asia was radically different from equatorial Africa. Instead of relentlessly blocking radiation, you now desperately needed to absorb whatever weak UV you could get. Suddenly, the dark skin that had been perfect in Africa became a problem in the north, not because of cancer. The cancer risk at northern latitudes with weak UV was much lower. Not because of folate, less UV meant less folate destruction, so that was fine. The problem was something else entirely: vitamin D. Vitamin D is synthesized in the skin when UVB radiation hits a compound called 7-dehydrocholesterol. Your skin is literally a solar panel. It uses sunlight as an energy source to manufacture this essential molecule. Vitamin D is not optional, not even a little bit. It is absolutely fundamental to human health. It regulates calcium and phosphorus absorption in the gut. Without vitamin D, those minerals don't make it into your bloodstream. Without it, calcium doesn't get properly absorbed, no matter how much dairy you consume. Without calcium, bones don't mineralize correctly. They stay soft and weak. In children, severe vitamin D deficiency causes rickets, a disease that softens and deforms the bones, bowing the legs outward. Rickets flattens the skull, bows the legs, and stunts growth, a devastating cascade of deformities. In adult women, vitamin D deficiency can cause osteomalacia, which softens the pelvic bones. A deformed pelvis makes childbirth extraordinarily dangerous. The baby's head can't pass through the birth canal. Women with severe vitamin D deficiency had dramatically higher rates of death during labor, a brutal evolutionary filter. Vitamin D deficiency also impairs immune function, making you more susceptible to infections and weakens muscle strength. Vitamin D deficiency doesn't stop at the skeleton, it also impairs immune function, making you more susceptible to infections and affects muscle strength and cardiovascular health. Some research links chronic deficiency to depression and cognitive decline. Vitamin D does so much biological work that when you run out of it, the body starts failing in multiple systems simultaneously: bones, immune system, muscles, brain, all at once. Now put a dark-skinned person in northern Europe 40,000 years ago. They have highly efficient melanin, a perfect shield for Africa, but in the gray, overcast, low-light north, that same melanin becomes a trap. Their skin blocks UV radiation beautifully, which was brilliant in Africa, but now it's blocking the very UV they need to synthesize vitamin D, a molecule essential for survival. Their skin can't tell the difference between dangerous UV it should block and useful UV it desperately needs. It just blocks everything indiscriminately. So they don't make enough vitamin D. Their skin, designed to protect, now starves them of the very resource they need to stay alive. Their calcium absorption drops, their bones weaken, their children develop rickets with bowed legs and flattened skulls, and women die during childbirth from deformed pelvises. In a pre-industrial world with no supplements, no fortified food, no medical interventions, dark skin in northern latitudes wasn't just a disadvantage, it was a death sentence stretched across generations. An evolution, that cold, merciless, endlessly patient calculator, started selecting against it. The algorithm had simply reversed its inputs. Mutations that reduced melanin production began appearing in the population randomly, as mutations always do, by chance in the genetic code of individuals. But instead of being eliminated, these mutations spread because individuals with slightly lighter skin synthesized slightly more vitamin D, had slightly healthier bones, and had slightly higher reproductive success. Generation after generation, slightly lighter, because in that northern environment, lighter skin meant more vitamin D, healthier bones, and more offspring. The algorithm had simply reversed its inputs. Generation after generation, the same pattern repeated. Slightly lighter skin, slightly more vitamin D, slightly healthier bones, slightly more surviving children. Over thousands of years, the average skin tone of northern populations drifted upward, not because anyone decided it should, but because in that environment, lighter skin kept more people alive. The algorithm had simply reversed its inputs. In Africa, dark skin was the winning move. In the north, light skin was the winning move. Same sun, different latitude, different answer. For a long time, scientists assumed the depigmentation of European populations happened gradually over hundreds of thousands of years, a slow, steady drift. But recent ancient DNA analysis has completely demolished that assumption and replaced it with something far more interesting. Early European hunter-gatherers, the people who lived in Europe for tens of thousands of years after the initial migration out of Africa, were still significantly dark-skinned. Even after living at northern latitudes for a very long time, they hadn't dramatically depigmented. The change was slow, not sudden. The most famous example is a specimen known as Cheddarman, a name that sounds like a cheese platter but represents a pivotal piece of the puzzle. He lived in what is now Britain approximately 10,000 years ago, right around the time the last ice age was ending and the landscape was changing. Ancient DNA analysis published in 2018 revealed a surprising combination. Cheddarman likely had dark to medium dark skin, dark curly hair, and blue eyes. That combination looks almost paradoxical to modern eyes. We've come to associate blue eyes with very pale skin, but that's a very recent link. But 10,000 years ago, blue eyes with dark skin was perfectly normal. The genetic link between pale skin and blue eyes came much later. The extremely fair skin that burns in about 12 minutes of summer sun, the kind associated with northwestern Europeans today, is far more recent than most people realize. This ultra-pale skin spread widely across European populations only in the last 6,000 to 8,000 years, a blink of an eye in evolutionary time. In the full 300,000-year history of Homo sapiens, that 6,000 years represents less than the last 3% of our existence. So what happened 6,000 to 8,000 years ago that suddenly accelerated the spread of pale skin so dramatically? The answer is one of the biggest transitions in human history, the Neolithic Revolution, the switch from hunting and gathering to farming. When humans transitioned to agriculture, their diet changed completely and permanently, shifting from a diverse wild menu to a narrow set of cultivated staples. Hunter-gatherers ate a varied diet that naturally included significant amounts of vitamin D from fatty fish like salmon and mackerel, and organ meats like liver and kidney. They also ate shellfish and other animal products that are among the richest dietary sources of vitamin D in existence. Farming populations, by contrast, ate mostly cereals, wheat, barley, oats, rye, carbohydrates with hardly any vitamin D at all. Their dietary vitamin D intake didn't just drop, it collapsed, because these staple grains contain virtually none of the vitamin. Suddenly, populations that have been getting by with modest UV synthesis because their diet also contributed were now almost entirely dependent on whatever their skin could produce. If their skin was still fairly dark, that wasn't enough. The melanin blocked the weak northern UV, and vitamin D deficiency set in. The selection pressure for lighter skin intensified dramatically. Suddenly, even tiny advantages in vitamin D synthesis became a matter of life and death. Even the smallest reduction in melanin, a slightly lighter shade, became critically important. It meant your skin could capture just a bit more of that scarce northern sunlight. But there was a second factor that made this change happen faster. It wasn't just diet, it was how people lived together. Farming communities were large, dense, and sedentary. Instead of small, scattered bands, people now lived in villages of hundreds, packed together in permanent settlements. Population size and density have enormous effects on how quickly an advantageous mutation can spread through a gene pool. More people means more chances for a new trait to take hold. In a small, scattered hunter-gatherer band of 50 people, a beneficial mutation might take a very long time to reach even neighboring groups. It could easily get lost entirely. But in a dense farming village of hundreds, connected to a network of other villages, a beneficial mutation could spread through thousands of descendants in just a few generations. The combination dietary vitamin D collapse plus population density essentially hit the fast-forward button on European depigmentation. Within a few thousand years, the selective pressure that had been quietly nudging skin tones lighter for tens of millennia suddenly became intense, rapid, and visible in the archaeological record. Here's something that genuinely surprises most people when they first hear it. Skin color is not controlled by a single gene. There is no single dark skin gene or light skin gene. There is no single dark gene versus light gene where one dominates the other. It's far more complicated than that. The idea of a simple switch is a myth. Skin pigmentation is a polygenic trait. It's controlled by dozens of different genes working together, each influencing melanin production, type, and distribution in complex ways. These genes control how much melanin your skin makes, what type eumelanin or pheomelanin, how the pigment granules are distributed inside your cells, and how your skin responds to UV exposure over time. Here's what makes this truly remarkable. Different populations that independently evolved lighter skin did not use the same genes to do it. East Asians and Europeans both developed significantly lighter skin than equatorial Africans, but the genetic variants responsible are largely different between the two groups. They arrived at similar outcomes through completely different molecular routes. Think of it like two architects building the same house but using different blueprints and materials. This is called convergent evolution. The same adaptive solution discovered independently by separate populations facing the same environmental challenge. The same solution, lighter skin in low UV environments, was found independently by populations on separate continents through entirely different genetic pathways. The evolutionary pressure was so strong, so consistent, so unambiguous, that natural selection found the same answer multiple times, not once, not twice, but repeatedly. When evolution keeps reinventing the same trait from scratch across different populations using different genetic tools, that's as strong a signal as biology ever gives you, that the trait truly matters for survival. While we're in the genetic neighborhood, let's talk about something equally mind-bending. Blue eyes. Every single person alive today with blue eyes, every one, no exceptions, descends from a single individual who lived somewhere around the Black Sea region, approximately 6,000 to 10,000 years ago. One person, one mutation, one moment. Before that individual was born, the entire human species had brown eyes. Everyone. Brown. Brown, nothing but brown as far back as you go. Then this one mutation appeared, a change that reduced melanin production specifically in the iris, and it spread, slowly at first, then faster because it was probably genetically linked to skin pigmentation variants under strong selection. Then one mutation appeared, a tiny change that reduced melanin production specifically in the iris, and it spread. It spread because it was probably genetically linked to skin pigmentation variants that were themselves under strong selection for lighter skin. Blue eyes are younger than agriculture, younger than Stonehenge, younger than the domestication of the horse. Traits we treat as ancient and primordial are, in geological or evolutionary terms, basically brand new. Step back and look at the full picture. Skin color, the thing that has defined so much of human history, is at its core a UV calibration system. It is a dial, your body's best ancestral estimate of how much sun protection you need, given the latitude your ancestors inhabited, the diet they ate, and the sun they lived under.